We are live, sir. You can start.
Hello everyone, welcome to the GATE Academy again. How are you all? I hope all of you are doing fine and your preparation is going good. Tell me, how is your GATE preparation going on? As November has started, like today's 1st of November, right? So we have approximately 3 months left because in the mid-Feb your exam will be there, right? So we have approximately 3 months. So I'm not counting that half month because there will be some holidays like Diwali holidays and Christmas holidays and New Year holidays. So definitely you'll take rest and you'll do some kind of party. So tell me, how is your preparation going on? All of you? Yeah. So definitely you will be enjoying this GATEvantage sessions because we are doing for each and every subject so that you can understand the important concept and you can revise those important concepts, right? So recently we had taken for the heat transfer also. I had taken this GATEvantage session of heat transfer in which we have discussed about lump parameter analysis and these kind of things. And we have taken one more session on the heat transfer in which we have discussed about the internal force convection, or I can say the internal flow. So in which we have discussed about so many things about convection and we understood so many important questions which came in the previous year GATE exam. Yeah, hi Bhavesh, how are you? Okay, so today we are going to start a session of thermodynamics, and in this particular session we are going to discuss concepts of entropy, because as you know that entropy is one of the most important topic in the basic thermodynamics, right? So similarly we have one more session planned, that is tomorrow. That is in that particular session we are going to discuss Brayton cycle, because I selected this topic because there are so many questions in the previous year GATE. If you see the previous year GATE questions, so there are so many questions from the Brayton cycle, so it is very important. So in the tomorrow session we are going to discuss Brayton cycle, but in today's session we are going to discuss entropy. Actually, tell me one thing: do you feel that entropy is a tough topic? I just want to know from your side. Do you feel that entropy is a tough topic? Yes or no? Bhavesh, for crash courses we'll try to do it. Don't worry, yeah. Definitely, we'll try to do it, and we are planning for this also. But I cannot guarantee you. But definitely, we'll try to do this. Actually, tell me one thing: do you feel that entropy is a tough topic, all of you? Because I can see there are some people who are watching me. So can you tell me that? Do you really feel that entropy is a tough topic? A very tough topic, but it's not. It is not a tough topic actually. What happens is generally students get confused in this particular topic. That's why they feel like this is a tough topic. Okay. Whole thermodynamics is tough. Don't worry, yeah. Definitely, I will try to explain you in a simple manner. It's not like that thermodynamics is tough. Thermodynamics is the basic subject of engineering, yeah. We study thermodynamics in the third semester, right? So why we study in this third semester? Because it is a basic subject. So that's why we start from the basic of from the beginning of the engineering. We study the subject in the beginning of the engineering because it creates the base of the other subjects like IC engines, power plant, and refrigeration, air conditioning, right? So that's why it's not a tough subject, it's an easy subject. Only you need to understand the concepts of the thermodynamics. Actually, if you see the first law and second law of thermodynamics, that are those are not the laws of thermodynamics, those are the laws of nature. If you see the first law of thermodynamics, that is the energy conservation, which is true in every case. Okay, we cannot deny the energy conservation. So कहते ना ये सत्य वचन है, ठीक है? That first law of thermodynamics is not, it is not the law of thermodynamics, it is the law of nature. Only you need to understand the basic things about thermodynamics, then only you will, and you have to feel the thermodynamics with the help of some real life examples. Then only you will be able to understand the depth of the thermodynamics, otherwise you will find it very difficult. Okay, if you connect all the things with the real life examples like systems surrounding all these things, see, these are the basic things. But if you connect with the help of some real life examples, so definitely it will be very easy for you to understand. But don't worry, today we are going to start entropy, and definitely I will try to make sure that after that you will be able to solve all the questions which are there in the previous year GATE exam after attending this session. Okay, so I will try to explain you a little bit about the physical significance of entropy also, because that is completely connected with the available energy. Okay, actually what happens in the entropy chapter, if you study the entropy chapter in the books and anywhere or in any class, so initially we understand the mathematical significance of entropy. First of all, we learn how to calculate entropy change in different processes, how to calculate entropy generation in a different processes. After that, when we connect that entropy with the available energy, then we will be able to understand that why we calculated entropy generation and why we calculated entropy change of a system in a particular process. Okay, so entire thermodynamics is the connected subject. It is like a chain. So if you suppose if you are not studying the entropy and you want to understand the available energy, then you will not be able to understand why we are studying the available energy. And if you're studying entropy and if you're not studying the available energy part, then definitely you will not be able to understand why we are going to study this entropy. So I will try to explain you with the help of available energy also that why we are studying this entropy. Okay, so let's start. So we are skipping the derivation part because here we are not interested in the derivation part, because in the GATE exam nobody will ask you the derivation part, right? So here we are just starting the basic equation. We are starting from the basic equation of entropy, which you are definitely you must be aware about it, right? So let's start. Just a second, let me reorganize this. Yes, now we'll start. So entropy, first of all, you need to understand that entropy is a property of a system. Entropy, it is a property of a system, and we are always interested in the change in property of the system. Okay, just like change in internal energy, change in enthalpy, change in temperature. Because what happens when we study thermodynamics, when we study different process, what happens, our system goes from state 1 to state 2. Okay, we are never interested in the absolute value of any property. We are never interested in that. We are always interested in the change in property, like change, what is the change in volume when the system goes from here to here? What is the change in pressure when the system goes from here to here? What is the change in temperature? What is the change in internal energy? What is the change in total energy? What is the change in enthalpy? We are interested in the change because what we want that what is the change in these two states. That's why we are interested always in the change in properties, right? We are not interested in the what is the absolute value of any property at this point and what is the absolute value of any property at this point. Okay, we are not interested in that. We are always interested in the change, right? Similarly, we are always interested in the change of property. Change in entropy. We are always interested in the change in property, and that's why we always calculate the change in entropy. That system is going from one state to another state. Then what is the change in entropy? And I'm giving you one statement here, which you will be able to understand almost 1 hour later. Okay. So what happens? Entropy represents the amount of unavailable energy, unavailable energy associated in a particular process. What I'm saying, that your entropy represents the amount of unavailable energy associated in a particular process. Please remember the statement. I will give you the one of the best example for this so that you will understand. So what is entropy? The physical significance of entropy is that entropy represents the amount of unavailable energy associated in a particular process. Now the question comes, what is the unavailable energy? So I will tell you later, but I'm just making a statement here. So later I will prove the statement also. That entropy signifies or entropy represents the amount of unavailable energy associated in a particular process. Okay, we'll understand this, don't worry. So let's start from the basic equation of entropy, that is change in entropy. ds. Entropy we represent with the sign is S. We represent entropy as S, just like internal energy as U. We represent entropy as S. It is given by del Q by T plus entropy generation. So I'm writing this entropy generation as delta generation. This is the basic equation you must have studied, right? What is this? This is the change in entropy of a system. This is the change in entropy of the system when your system is going from state 1 to state 2, right? This is change in entropy. Now, what is this? This is the change in entropy due to heat interaction. See, this ds. ds is the change in entropy because I told you that entropy is a property, right? Entropy is a state function. It is not a path function. Entropy is a property, and all the properties are point function. That means state function, right? It does not depend on the path followed by the system, right? So entropy is a property, you know. So ds means change in property from state 1 to state 2. The change in entropy of system. So it is combination of two things, that is del Q by T plus delta S solution. Now what is this del Q by T? This is change in entropy associated. This is the change in entropy associated due to heat interactions. Due to heat interactions. Due to heat interaction. And now this term represents that is change in entropy. Yeah, entropy generated. Entropy generated due to irreversibility. Irreversibility within the system. Irreversibility within the system. So this is the basic equation we have. This is the basic equation we have. Now try to understand, whenever we are talking about a reversible process, whenever we talk about a reversible process, okay, whenever we talk about a reversible process, a reversible means internally reversible. Reversible means internally reversible, means there is no irreversibility. There is that means I can say there is no friction inside the system, or there is no lack of equilibrium inside the system. So for internally reversible process, this delta S generation is equal to 0. Because if the process is internally reversible, means there is no irreversibility inside the system. Okay, if there is no irreversibility inside the system, means there are no losses. And if you understand this entropy, entropy signifies the losses. The more the entropy, the more the losses. The less the entropy generation, the less the losses. So if there is no losses inside the system, then that means there is no friction, there is no lack of equilibrium. So in that case, the entropy generation will be 0. Now, if the process is internally irreversible, that means there are some friction losses, there are some lack of equilibrium for internally irreversible process. There will be some entropy generation because there will be some losses. So entropy generation will be greater than 0. So by these two statements, what I can write, that your entropy generation is always greater than equal to 0. Okay, the entropy generation is always greater than equal to 0. Now I'm trying to explain you in a simple manner. Let's say we have a process on any xy axis. Let's say we have a process on any xy axis, maybe PV, TS, HS, any curve. Okay, any, I'm not telling you the coordinates. It can be any curve. It can be any curve. Okay, let's say xy axis we have, and there's a process like this. As I told you, let's say it is a TS diagram. It is a TS diagram. Okay, let's say it is a TS diagram. So we know what we know, that's from state 1 to state 2, your change in entropy is fixed as 2 minus S1 because it is state function. Doesn't matter which path is follows because it is a state function. So suppose it is going from this to this path. Okay, or it is going from this path. It can follow any path, but the change in entropy will be constant. Okay, but when you see the entropy equation, ds equal to del Q by T plus delta S generation. This is your ts, this will be constant. This ts, this will be constant. But this can vary. Del Q by T can vary, delta S generation can vary. Now, why it varies? Because when the process is more irreversible, when the losses are more, then your entropy generation will be more. Okay, this I will connect with the help of irreversibility also, don't worry. Okay, this I will connect with the help of irreversibility also. So the more the or I can say the more the irreversibility associated or more the losses are there in the process, your delta S generation will be more and the process will be more irreversible. Okay, so this is the basic concept of entropy. Actually, there are so many things which you will understand when I will be giving you an example of a heat engine. Okay, so just wait for some time so that definitely you'll be able to connect all the things. Okay, now let's move further. So this is a simple equation, basic equation we have. The change in entropy of the system will be equal to del Q by T plus delta S generation, where this Ts represents the change in entropy of the system, this del Q by T change in entropy of the system due to heat interaction, and this delta S generation will be nothing but entropy generation due to irreversibility within the system. Okay, now we'll do some entropy analysis of a closed system. Okay, now we'll do entropy analysis for a closed system. Entropy analysis for a closed system. for a closed system. Now, what is the basic equation we have? That is change in entropy will be equal to change in entropy due to heat interactions plus entropy generation. Now we have two cases. Case 1. Please understand it with your full consciousness, because there are so many things you will get to know if you understand this. So now, if the process is internally reversible, if the process is internally reversible, so that means your delta S generation will be 0. So your change in entropy of the system becomes only del Q by T. Now, if there is a heat addition process, now there can be three cases. If heat is added in the system, if heat is added, so if heat is added, your del Q it will be positive. So your change in entropy will be also positive. Now, if the heat is rejected, if heat is rejected, then your del Q will be negative and your change in entropy will also become negative. The third case will be if process is adiabatic or no heat interaction is there. If no heat interaction is there. If no heat interaction, so that means your del Q will be equal to 0 and the change in entropy of the system will be equal to 0. So when the change in entropy of the system is 0 in a particular process, then that process is called as isentropic process. Then that process is called as isentropic process. So for the isentropic process, see here, process is internally reversible. So generally the internally reversible process is usually called as reversible only. We don't use internally word because it is too lengthy, right? So in general, whenever we talk about a reversible process, we always say that it is internal. Whenever we talk about a reversible process, it is by default internally reversible. Internally reversible means there is no lack of equilibrium, there is no friction inside the process, right? So that is the meaning of internally reversible. So whenever we say that process is reversible, we are only talking about internally reversible process. Now, what is externally reversible process? Externally reversible process means there is no interaction with the surrounding. Okay, there is no heat interaction with the surrounding. That will be called as externally reversible process. Means externally reversible means no irreversibility is coming inside the system from the surrounding, or no irreversibility is going or simply because irreversibility can come inside the system, it cannot go outside the system, right? So suppose if some irreversibility is coming from the surrounding inside the system, then it is called as externally irreversible. But when there is no interaction between the system and surrounding, then no irreversibility can come inside the system, so the process will be called as externally reversible process. So if you combine these two, internally reversible and externally reversible, the process is called as totally reversible. So it is completely different concept. We are only interested in the reversible processes. What is the reversible process? We are talking about internally reversible process. Reversible process means we are talking about internally reversible process. Okay, reversible process by default means internally reversible process. Okay, so whenever we say that the process is reversible, that means internally reversible, and the process is adiabatic. So whenever we say process is reversible and the process is adiabatic, it must be isentropic, because we have proved here this process is reversible, this process is adiabatic also, so it is coming as isentropic. Okay, so now come to the second case, case 2. Case 2 is if process is internally irreversible. Case 2, are you getting my point? Yes or no? All of you, are you getting my point? Yes or no? If the process is internally irreversible, when the process is internally irreversible, then definitely your delta S addition will be greater than 0, because it cannot be negative. Okay, when we derive this particular equation, d is equal to del Q by T plus delta S generation, then the mathematics says that delta S generation must be greater than or equal to 0. It cannot be negative value. Okay, so if the process is internally irreversible, then delta S generation is greater than 0. So the basic equation becomes ds equal to del Q by T plus some positive value, right? You know, so here also we have three cases when heat is added. When heat is added. So when the heat is added, so you will see a change in entropy will be some positive value plus some positive value, which will result in only positive value, right? When your heat is rejected, so in that case, when your heat is rejected, so definitely this del Q by T will be having some negative value and this delta S generation will have some positive value. Now here, three cases can be possible. Here, three cases can be possible when negative is more than positive. When negative is more than positive, so we'll be getting final value as negative. B, when negative is less than positive, then it will be having some positive value. When negative and positive will balance each other, it can be a case now when negative and positive are same, means they balance each other. So your entropy will become zero. Means in this particular case, we are having ds equal to 0, means it is an isentropic process again. It is isentropic. But what we can see here, for this isentropic process, the process is not even reversible, the process is not even adiabatic, right? But here, what we got, when the process was reversible and adiabatic, the process was isentropic. Okay, but for isentropic process, it is not necessary that process should be reversible and adiabatic. Okay, the process can be irreversible and adiabatic also. Okay, that means there can be heat transfer and there can be some internal irreversibility. In that case also, some or I can say, in that case also, it can be an isentropic. Okay, for an example, if you take an example, suppose you have a cup of tea. Okay, suppose you have a cup of tea and you are mixing this cup of, you are stirring this cup of tea like this. So what is happening due to some internal irreversibility? So some entropy is generated, but at the same time, heat is transferred to the surrounding, right? At the same time, heat is transferred to the surrounding. So due to this heat interaction, whatever the entropy is decreased, and due to the stirring process, whatever the entropy is increased, if both are same, then it can be an isentropic process, right? It can be an isentropic process. So for that isentropic process, the process need not to be reversible and adiabatic, but a reversible and adiabatic process will always be isentropic. Are you getting my point? Yes or no? So it is an important result, beta. So reversible and adiabatic process will be always isentropic, but for isentropic process need not to be reversible and adiabatic. Are you getting my point? Yes or no? Is that clear, everyone? Now the third case was adiabatic, means no heat interaction. No heat interaction. Are you getting my point? Yes or no? Are you able to understand this point? Oh, no heat interaction. Okay. So in this case, when the no heat interaction is there, so if we calculate the change in entropy, so this term will be 0 because del Q is 0 plus delta is generation some positive value, so it will be having some positive. So now here we need to understand one important thing, that change in entropy of a system can be positive, can be negative, can be 0. Means there is no limitation on the change in entropy of a system. There is no limitation on the change in entropy of the system. It can be, it can have some positive value, it can have some negative value, and it can be some, it can have some 0 value. But where is the limitation? Limitation will be on the entropy generation, because entropy generation cannot have negative value. Okay, entropy generation cannot have negative value. Okay, so these are some important things which you know. So now we are interested in calculating change in entropy of an isolated system. So once you understand this particular point, that is how to calculate change in entropy of an isolated system, you can easily calculate entropy generation for any process. Okay, only you need to understand this, how to calculate change in entropy of an isolated system. So let's say sorry, change in entropy of an isolated system. Please be focused here, because it is a very important thing. Change in entropy of an isolated system. So now, if we talk about change in entropy of an isolated system, we have basic formula that change in entropy of system is given as del Q by T plus delta S generation, right? So for an isolated system, what you know that there is no energy interaction. So definitely heat interaction will be 0, right? So the change in entropy of an isolated system is given as only due to entropy generation. And we know this entropy generation is always greater than or equal to 0. So definitely what we can say that is change in entropy of an isolated system must be greater than or equal to 0. Okay. Also we can write, because universe is an example of an isolated system. So change in entropy of universe is always greater than or equal to 0. So this is the principle of entropy increase. This is the principle of entropy increase. So that means, because I was from Hindi medium in the 12th class, I have studied in the Hindi medium up to 12th class. So there was a law that Brahmand ki entropy nirantar badhti rehti hai. So that's what I have studied in the 12th class. So that the entropy of the universe always increases. It cannot decrease. So that is the statement coming from here. This is the like I said, this is a statement of one of the statements of the second law, that the entropy of the universe can never decrease. It can be 0 or it can be positive. It cannot be negative. And when it will be 0, when your entropy generation will be equal to 0, and when the entropy generation will be 0, when all the processes in the isolated system or in the universe will be reversible. Okay, when all the processes in the universe will be reversible, then we can say the change in entropy of the universe is equal to 0. But we know that in the universe, all the processes are irreversible. Okay, reversible process is always hypothetical. So here, change in entropy of an isolated system, or I can say change in entropy of universe, is always greater than 0. Okay, always greater than 0. So here, one more thing we understood, that if we talk about change in entropy of a system, if we talk about change in entropy of system, it can be positive, it can be negative. But when we talk about change in entropy of the universe, it cannot be negative. Okay, so this is the limitation applied on the change in entropy of the universe in the second law of thermodynamics, that your change in entropy of the universe cannot be negative, it will be positive only when the processes are irreversible. But in the hypothetical case, when the processes are reversible, then your change in entropy of the universe can be 0. So now, this you must remember, that what is the entropy. See, whenever you want to calculate, see here what we have done, whenever you want to calculate change in entropy of the universe or entropy generation in a particular process, both are same thing. If you see here, if you remember this thing, if you observe these two things, that what is entropy generation? See, this is the method to calculate the entropy generation. This is a particular method to calculate the entropy generation, because whenever you want to calculate the entropy generation, what you have to do? You have to calculate the change in entropy of the universe. Now, what is the change in entropy of the universe? That is change in entropy of the system plus change in entropy of the surrounding. Now, suppose there are more than one system. So change in entropy of the system 1 plus change in entropy of the system 2 plus change in entropy of the surrounding. Okay, so this is the method to calculate entropy generation in a particular process. This is a method to calculate entropy generation in a particular process. Okay, so what is the change in entropy of the universe? That is change in entropy of system plus change in entropy of the surrounding. Either you can write like this, or change in entropy of the all interacting systems. Okay, both are same thing. Both are same thing. Just I told you, na, suppose you consider surrounding as one another. Suppose there is one system, one surrounding. Whether you can consider it as a system plus surrounding, or you can consider it as system 1 plus system 2. So both are the same thing. Doesn't matter. Okay, it is just a perspective. Whether you consider surrounding as a system 2 or surrounding as surrounding 1. It is just a perspective. The point is, you need to know how to calculate the change in entropy of the all systems. That's it. Okay, so this is the method to calculate change in entropy of the universe, or I can say entropy generation. So whenever you want to calculate entropy generation in a particular process, suppose there is a heat engine and there is some energy interactions are going on. So assume a universe. So whatever the heat engines, like higher temperature, that fluid which is flowing in the engine, and the lower temperature, assume these three as a three systems, system 1, system 2, system 3. Okay, you can do like this. So whenever you want to calculate the entropy generation, just assume one universe and take all the systems which are given. Okay, or you can calculate change in entropy of system 1 plus change in entropy of system 2 plus change in entropy of system 3, and suppose there are n number of systems, so the change in entropy of all the systems will be equal to entropy generation. That's it. So this is a particular method, okay, by which you can calculate change in entropy of any process, or I can say entropy generation in any process, or entropy change of the universe in any process. Okay, So it's the simplest thing. Now you need to know how to calculate the change in entropy of the system and how to calculate the change in entropy of the surrounding. Okay, this is the important thing here. So let's say a system can be anything. Yeah, system can be some ideal gases flowing from one point to another point. Piston cylinder assembly. So generally we deal with ideal gases, right? Generally we thermodynamics we are more concerned with the ideal gases. So first of all, we'll try to understand how to calculate the change in entropy for ideal gases, right? Sorry. First of all, we'll understand how to calculate change in entropy of ideal gases. Change in entropy of ideal gases. This is one of the important thing because there are so many questions in the GATE exam, and these are the direct formulas. These are the direct formulas. You can remember the direct formulas. Okay, from where we are getting these formulas? We are getting these formulas from the TDS equation. So there are two TDS equation we know. The first TDS equation is TDS equal to du plus PdV. Okay, TDS equal to du plus PdV. So now if you want to calculate this change in entropy, so divide this here T plus PdV by T, or I can write du equal to mCv delta T by T, mCv dt by T, mCv dt by T plus PdV by T means PdV equal to if you see this ideal gas equation, PV equals to MRT, right? So what I can write, because we know PV equals to MRT, so P by T will be what? MR by V, right? So it will be MR dV by V. So I am calculating change in entropy from state 1 to state 2, from 1 to 2. So it will integrate this entire equation from 1 to 2. Okay, so I'll be getting S2 minus S1, that is change in entropy from state 1 to state 2. S2 minus S1 will be equal to mCv ln T2 by T1 plus MR ln V2 by V1. mCv ln T2 by T1 plus MR ln V2 by V1. Okay, so this is the formula of change in entropy for ideal gas. This is the formula for change in entropy for an ideal gas. Okay. Similarly, we have another TDS equation, that is TDS equal to dH minus VdP. Okay, so if you apply the same things here, if you transfer T here and you will calculate with the help of integration, so you'll be getting a formula here like S2 minus S1 equal to mCp ln T2 by T1 minus MR ln P2 by P1. Okay, so these two formulas you can remember directly. Okay, these two are very important formulas because there are so many questions in the GATE exam on the basis of these two formulas. These two formulas are very important for the change in entropy of an ideal gas. Okay, these two formulas are very important in the change in entropy of an ideal gas. Okay, so remember these directly. Okay, these are very important. Now there's one more formula on the basis of these two. So if I rewrite this particular formula, so it will become S2 minus S1 equal to see here, how you can write T2 by T1, because we know P1 V1 equal to MRT1 and P2 V2 equal to MRT2, right? So I can write T2 by T1 equal to P2 V2 by P1 V1, right? So here I can write S2 minus S1 equal to mCv ln P2 V2 by P1 V1 plus what I can write R is R equal to Cp minus Cv. R equal to Cp minus Cv. Cp minus Cv log V2 by V1. Okay, so I'm rearranging this again. So what it is becoming, S2 minus S1 equals to mCv ln P2 by P1 plus mCv ln V2 by V1 plus mCp ln V2 by V1 minus mCv ln V2 by V1. Okay, so here you can see two terms will be cancelled out. Which one? This mCV ln V2 by V1. This is mCV ln V2 by V1. Okay, so now what is remaining? Final. Sorry, S2 minus S1 will be equal to mCV ln P2 by P1 plus mCP ln V2 by V1. mCV ln V2 by V1. Okay, so this is also another formula. You can remember these three formulas directly for change in entropy of an ideal gas. Okay, because there are direct question in the GATE exam from these formulas. Okay, so that's why these formulas are very important. This S2 minus S1 mCV ln T2 by T1 plus MR ln V2 by V1. This mCP ln T2 by T1 minus MR ln P2 by P1. And this third one is mCV ln P2 by P1 minus MR ln V2 by V1. mCP ln V2 by V1. So here you have to practice these formulas, because then only you will remember, because otherwise it will be very confusing where will be plus and where will be minus. So once you write these formulas 2 to 3 times in your notebook and in your rough note, so definitely you will remember these formulas. Okay, so I will tell you the best method to practice the formulas. Okay, so whenever you suppose if there are some formulas and you're getting any kind of confusion in the formula and you're not able to remember those formulas, just practice these formulas at least 10 times, 20 times. Write these formulas again and again and again and again. Okay, so what will happen? Your pen will remember this formula. Okay, so if you write a particular suppose let's say if you are writing a particular formula for 50 times, is there any chance that you will forget that? Not at all. Okay, if you write a particular formula like a plus b whole square, okay, just I'm taking an example of a plus b whole square, because we have written this formulas I don't know how many times, right? A plus b whole square, a square plus b plus b square. I don't know anybody will do any mistake in this particular formula, because we have used this particular formula so many times since our childhood, right? Similarly, there are some formulas, so why we get confusion? Because we don't practice it. As simple as that. If you practice a particular formula for 50 times, if you write a particular formula straight for the 50 times, so how you will forget that? Okay, suppose if what will happen, then it will go in your subconscious mind. So whenever you will writing that formula, now suppose there is some plus minus confusion, so automatically you will write that yes, here it is negative, here it is positive, because it is gone into a subconscious mind. Suppose a minus b whole square, you know that a square plus b square minus 2ab. So you already know that here it is minus, it is not plus. So whenever you're writing this formula, it automatically comes that yes, a square plus b square minus 2ab, because we are writing the formula of a minus b whole square. Okay, similarly here also. So where is CV, where is CP? So if you have the confusion to in remembering these formulas, please practice it. Okay, there is no shortcut to remember these formulas. Or if you can make any kind of logic, while remembering these formulas, that will be good. Suppose if you want to remember these two formulas, how I remember when I was preparing for the GATE exam in 2015 and 16. So at the time, I used to use some logic. Suppose there is CV, there is CP, right? There are two formulas. Here it is CV, here it is CP. So whenever there is CP, so here will be volume. Whenever there is CP, here will be pressure. See how I remember these formulas. See, we know that, see, this is nonsense logic, I know, but yes, this logic works for me. So that's what I'm telling you. So if you want to remember it, it's up to you. So here is CV and here is CP. So we know CP is always greater than CV, right? We already know that CP is always greater than CV. So we are approaching some value. Let's say CP, generally we remember CP for air like 1.005, CV for air is 0.718. Now we want to reach some mid value of CV and CP. So definitely I have to add something in CV so that I can reach that value, and I have to subtract something from CP so that I can reach that value. Okay. So I have to reach some mid value of CP and CV. So I have to subtract something from the CV and I have to add something in the CV. So then I will reach that particular value. So I remember like this. So whenever there is CP, I use negative sign. Whenever there is CV, I use positive sign. And here it is R, here it is R. Okay, so here is volume. So it will be log V2 by V1. Here it is pressure. So it will be log P2 by P1. And here with CV, it is log T2 by T1 only. Here it is log T2 by T1. So that's how I used to remember the formula. If you can make any kind of logic, doesn't matter how nonsense that logic is, but if it is helping you in remembering the formula, that logic will be absolutely fine for you. Okay, but there are so many formulas. It is just thermodynamics. There are, I think, 10-12 subjects in the mechanical engineering, and you need to remember all the formulas on your tips so that you can crack the GATE exam. So if you can make any kind of logic, so it will be great for you. Just like if you study the heat transfer, right? So there are some formula like when we do the analysis of fin. So like M, HP by K, there are some formulas. And like if you see the effectiveness of the fin, so there is like PK by AH. These are the formula. So when I was reading this effectiveness, so I think in 2016, so at the time PK movie was came. So this effectiveness PK by AH. So I remember like this PK mein Amir Khan hai. So that's why this is effective. Or PK mein Anushka hai. So that's why it is effective. So you can make any kind of logic. Doesn't matter how nonsense is this, but if you remember the formula with the help of that logic, so it will be good for you. So it's up to you whether you want to write this formula again and again, or you want to make some kind of logic. Okay, so it's up to you. It's entirely up to you. Okay, so I hope you are getting my point. So these are the three important formulas which are very important. Okay, and the third formula like CV and CP. So where it is CV, here will be pressure. Here it is CP. So here will be volume. Opposite. Okay, opposite. Volume, here volume. Pressure, here pressure. Opposite. Okay, so you can make any kind of logic. It's up to you. Okay, so now suppose if you want to calculate entropy associated with if you want to calculate during heating or cooling, entropy associated during heating or cooling. So entropy change associated, entropy change associated during heating or cooling. Okay, so we know that ds equal to del q by t plus delta S generation. So generally what happens, I told you that suppose there are two coordinates like ts diagram is there, and this is the process, and you want to calculate from S1 to S2, from 1 to 2, right? And you have to calculate change in entropy. Doesn't matter which path it is following. So definitely in between these two states, there will be a reversible path and there will be so many irreversible paths. Okay. So whether you calculate change in entropy with the help of reversible path, or you calculate the change in entropy with the help of irreversible path, doesn't matter. It will be same, because entropy is a state function. Entropy is a property, right? In between two fixed state, the change in entropy will be same. In between two fixed state, change in entropy will be same. Doesn't matter which path it follows. Okay, doesn't matter. It will be will it be a reversible path or will it be a irreversible path? Doesn't matter. The state change in entropy between two states will be always same. So what we are doing here, we are considering the process is reversible. So when we consider the process is reversible, so delta acceleration will be 0. And the change in entropy between state 1 and 2, we can calculate by assuming the process is reversible, and it will be equal to del q by t. So it will be equal to mc dt by t. Okay. So if you want to calculate, if you want to integrate this, so it will become S2 minus S1 will be equal to mc ln T2 by T1. So this is the change in entropy associated during heating or cooling. Okay, during heating or cooling for solid or liquid. Suppose some water is going from 20 to 80 degrees centigrade, then what will be the change in entropy? So this will be the change in entropy. Suppose some solid iron is coming from 300 Kelvin to 290 Kelvin, then what is the change in entropy? This will be the change in entropy. Okay, so that's how you can calculate change in entropy associated during heating or cooling. Okay, that's how you calculate during heating or cooling. Now suppose if I talk about some thermal energy reservoir, right? Entropy change for thermal energy reservoir or any phase change process. Any phase change process. How you will calculate it? Suppose if you want to calculate change in entropy of thermal energy reservoir, so ds is generally given as del q by t, because we are assuming the process is reversible. So for thermal energy reservoir, temperature remains constant. It is a property of thermal energy reservoir that doesn't matter how much amount of energy you how much amount of heat you supply to the reservoir, or you extract from the reservoir, its temperature remains unchanged, right? So change in entropy of a thermal energy reservoir is given as 1 by T into Q, del Q. Okay, because T is constant, so simply we can write it as Q by del Q by T. So this is same as del Q by T only. Okay, but here temperature will be your constant, right? So now thermal energy reservoir is a source. If your TER is source. Okay, so what happens in the source? Suppose this is the source is 400 Kelvin. So source supplies the heat energy. So that means if we talk about the source, so it is rejecting the heat energy, right? But because we are assuming the source is system, right? So what is the work of the source? It is the supplier of the heat energy. But if you think about the source, what is happening in the source? It is rejecting some heat. So for the source, change in entropy will be how much? Minus Q by T, where Q is the amount of heat supplied by the source. Now, when your TER is sink, when your thermal energy reservoir is sink, so what happens in sink? Sink means surrounding. So what happens in the surrounding? So heat is accepted by the surrounding. So if you think surrounding is a system, if you think or sink is a system, so what is happening in the sink? Heat is coming to the sink. So that means positive quantity. So that will be Q by T. Okay, where T is the temperature of the sink. Now, if we talk about a phase change process, okay, change in entropy for phase change. How you can write? That is change in entropy for phase change. Because phase change process is also considered as a reservoir. Why? Because at the time of phase change, there is a large amount of energy interaction or large amount of heat interaction, right? At the time of phase change, there is a large amount of energy interaction, like it's a large amount of heat interaction, but its temperature remains constant. Okay. But its temperature remains constant. So at the time, change in entropy of the phase change is given as whatever the amount of heat is interacted, that is Q, divided by the phase change process, and by the temperature of the phase change process. And the temperature of the phase change process is given as saturation temperature, right? So it is represented as Tsat. It is represented as Tsat. And the phase change energy, or I can say the heat required for the phase change, is called as latent heat, right? So it will be latent heat by saturation temperature. Latent heat by saturation temperature. So now I will give you some example so that you will understand. So whenever we study some TS diagram, let's say TS diagram or any PV diagram. So I'm taking an example of TS diagram. So this is the PV curve on the TS diagram. You can see here, this is the saturated liquid line. This is the saturated vapor line. This you must be knowing, right? So now suppose I have constant pressure line like this. Suppose it is isobar on the TS plane. Let's say it is 1 bar. Okay, and your water is changing phase from the saturated liquid to saturated vapor. And we know on the saturated liquid line, the properties are represented by subscript F, like SF, UF, HF, and here it is represented by SG, UG, HG. So now if you want to calculate the change in entropy, SG minus SF. See, I'm writing in the small terms, that means specific terms means per unit mass. So this is the capital S, so its unit is joules per Kelvin. So whenever I'm writing small s, so it is a specific term, specific entropy. So its unit will be joules per kg Kelvin, right? So that's why if you see the steam table, so their SF and SG are given in steam kilojoules per kg Kelvin always. Okay, whenever you see the steam table and you take the data from the steam table, HF also is given per kilojoule per kg, like kilojoules per kg. Entropy is given in kilojoules per kg Kelvin. Okay. So whenever you write the small terms like small h, small u, so that means the specific terms. Specific means per kg. Okay. So SG minus HF, SF, how you can calculate? That is the latent heat by saturation temperature. So let's say the saturation temperature is Tsat, and the latent heat is given as Hg minus HF by Tsat. Or generally, Hg minus HF is represented as HFG by Tsat. So I hope you are getting my point. And there is a beautiful question, 2 marks question in the GATE exam on the basis of this particular formula only. Only you need to take care of the units. There is a 2 mark question in the previous GATE exam in which only you need to take care of the units, whether you are taking in the per kg mass or you are taking in not per kg mass. Okay, so that you need to take care. Otherwise, there is nothing in that particular question. So that 2 marks question is given just to check whether you balance the units or not. Okay, so there's a beautiful question. We are going to do that. Don't worry about that. Okay. So now, initially, I told you, now here, I'm going to explain you some physical significance of the entropy. Initially, I told you that entropy signifies or entropy represents some amount of unavailable energy associated in a particular process. Okay. Entropy signifies, or entropy generation signifies the amount of unavailable energy associated in a particular process. So for this, for prove the statement, I am taking some example of a heat engine so that you will understand in a better way. So let's take an example of a heat engine. So you have some source and you have a sink and there is a heat engine. So let's say the source is at 1200 Kelvin and the sink is at 300 Kelvin. Okay, it is given as this source is supplying. It is given as some source is supplying 500 kilowatt. But please share this this particular session with your friends also, so that they will also get some idea about some important concepts in the entropy. So this Q1, let's say this Q1 is 500 kilowatt is given. This Q2 we don't know, and this heat engine is given. Okay, this is the heat engine, and also it is given that this heat engine is producing 180 kilowatt. Okay, 180 kilowatt. This heat engine is producing 180 kilowatt. So now you need to calculate what is the irreversibility associated. Now, first of all, need to understand what is the irreversibility. See, irreversibility simply means losses. Now, I want to explain you a little bit of concept of available energy and unavailable energy. See what happens whenever we have a system at some elevated state. Elevated state means it is having some different properties from the surrounding. Okay, whenever we have a system at some different state, so it is having some potential of doing work. Okay, doesn't matter whether the temperature of is less than the surrounding, temperature is higher than the surrounding, doesn't matter. Whenever the system is having different properties from the surrounding, then it is having some work potential always. So that means whenever the system is coming equilibrium with the surrounding, so that state is called a steady state. Okay, जब मर जाता है भैया तो सिस्टम काम कैसे करेगा? Okay, हम भी अगर मर जाएंगे तो हम चल फिर नहीं पाएंगे. So why we are still alive? Because we are having some energy, we are having some work potential, right? So similarly, if the properties of this system is some or I can say properties of the system are different from the surrounding, then definitely it is having some work potential, right? So what happens generally, I'm taking an example of heat engine. So suppose we have a higher temperature reservoir from which it can reject heat, and we have a lower temperature reservoir which can accept heat. So now suppose we have a body at high temperature which is rejecting heat, right? So what we can do with this heat? We can apply a heat engine between these two temperatures, that higher temperature and lower temperature, and we can extract some work. Okay, whenever we have a body at higher temperature, what we can do? We can extract some work by applying a heat engine between that higher temperature body and the surrounding. Okay, this we can do. Okay, so now what is the maximum work we can extract? When the engine is working on the Carnot cycle. When the engine is working on the Carnot cycle, so in that case you can extract the maximum work. Okay, and this is the limitation of the second law. Actually, you can say, like, we cannot convert entire heat into work. Okay, we can convert only a portion of heat into work. And what is the maximum portion of work, maximum portion of heat we can convert into work? When your engine will be running at the Carnot cycle, then only we can convert the maximum portion of the heat into work, and that will be called as your available energy. So like suppose we have a higher temperature body, you have a low temperature body, there is a heat engine, and this heat engine is working on the Carnot cycle, and at that time your work is produced, that is called as the maximum work produced, and that is called as your available energy. Okay, that is called as your available energy of the system. Okay, so suppose that efficiency, Carnot cycle efficiency is 50%. Suppose this is Q, so suppose this is 100 kilojoules, then definitely of the like this is 600 Kelvin, this is 300 Kelvin. So what will happen? Efficiency is 50%, Carnot cycle efficiency is 50%, W max will be equal to 50 kilojoules, and this 50 kilojoules will be lost. So this is the second law of thermodynamics. Okay, and now this maximum work which can be converted, it is the available energy of the system. But due to some limitations, due to some irreversibilities in the system, we cannot even extract that 50 kilojoules completely. Okay, because your engine is not running on the Carnot cycle. There are some irreversibility associated in the cycle. So we cannot convert this 50 kilojoules completely into work. Okay, according to second law, we can convert this maximum 50 kilojoules only. But due to some practical limitations, we cannot even convert this 50 kilojoules, this 100 into 50. There are some losses. So that loss is nothing but that is called as irreversibility. That loss is nothing but that is called as irreversibility. So I hope you are getting my point. What is this irreversibility? And this irreversibility can be calculated as T naught delta S generation. This irreversibility is calculated as T naught delta S generation. Now, in the same example, see, I'm explaining this example again. Suppose we have two temperatures, 600 Kelvin, 300 Kelvin, and 600 Kelvin is supplying 100 kilojoules, and let's say the cycle is working on the Carnot cycle. So what is the maximum work we can convert, because the efficiency of the Carnot cycle will be 1 minus T2 by T1, 1 minus 300 by 600, which will be equal to 0.5 or 50%. So definitely the maximum work we can get that 50 kilojoules, because it is having a 50% efficiency. Okay, just for example. But still, we cannot extract that 50 kilojoules. Why? Because due to some practical limitations, due to some friction, due to some lack of equilibrium, due to some internal irreversibility, blah, blah, blah. Due to that, we cannot extract that 50 kilojoules from that particular system. So it is even lesser than the 50 kilojoules. So let's say in actual scenario, what we are getting, let's say 45 kilojoules. We are getting only 45 kilojoules. In actual scenario, let's say we are getting only 45 kilojoules. So now what is the irreversibility, or what is the losses? 50 minus 45. That is 5 kilojoules. Okay, that is 5 kilojoules. So this is the irreversibility. Irreversibility is what? Loss of available energy. This is available energy was 50 kilojoules. So what is the loss of available energy? 5 kilojoules. And this loss of energy is nothing but irreversibility. Okay, so this is the one method to calculate the irreversibility, that when you know the maximum work potential minus actual work potential, so definitely it will be clear loss, because we can get maximum equal to this, but we are not getting the maximum. Okay, we are getting some actual work. So the difference of these two will be what? Irreversibility, or I can say loss of available energy. Okay, so difference of these two will be loss of available energy. But the same irreversibility we can get with the help of T naught delta S generation. The same irreversibility we can get with the help of T naught delta S generation. Now that I will show you in this particular example. I will calculate this irreversibility with the help of the concept, that is maximum work minus actual work, and with the help of the entropy generation, that is T naught delta S generation. Then only you will understand that yes, this entropy generation or entropy signifies the amount of unavailable energy associated. Unavailable energy simply means the loss of available energy or irreversibility. Okay, what is the unavailable energy? Because it is not available for us. Okay, the unavailable energy means the loss of available energy. In simple terms, unavailable energy means the loss of available energy. Are you getting my point? Yes or no? Are you getting my point? Yes or no? Now I will explain you with the help of this particular example. So let's say we have a heat engine which is having a higher temperature is 1200 Kelvin, lower temperature 300 Kelvin, and which is actually producing 180 kilowatts. Okay, and the heat supplied is 500 kilowatt. So now, if I want to calculate this irreversibility, which will be maximum work minus actual work. Okay, so now how to calculate the maximum work? Maximum work will be when your engine is working as a Carnot engine. So efficiency of Carnot engine will be equal to 1 minus T2 by T1, that is 1 minus 300 by 1200. Okay, or this efficiency will be equal to maximum work by heat supplied, that is Q1. Okay, so efficiency is how much here? 3 by 1 minus 3 by 4, that is 1 minus, how much it is? 1 minus 1 by 4. 1 minus 1 by 4 will be equal to 3 by 4. So 0.75 will be equal to W max by Q is how much? 500. So your maximum work is actually how much? 375 kilowatt. This will be your maximum work. But how much you are getting actual? 180 only. So what are the losses? That is, what is the irreversibility? W max is 375 minus actual is how much? 180. So that means 380, that is equal to 195 kilowatt. So due to the irreversibility of available or irreversibility associated in this heat engine, 195 kilowatt is lost. Okay, 195 kilowatt is lost. Okay, it happened. 195 kilowatt is lost. So now I will show you the same result with the help of entropy generation. I will show you the same result. Definitely, this I told you in the beginning now that entropy signifies the amount of unavailable energy or amount of irreversibility associated in a particular process. So definitely, it should give the same result, right? So I'm doing the same. So irreversibility can be calculated as T naught delta S generation. The T naught is the surrounding temperature. This is the sink is the surrounding here only because sink temperature, surrounding temperature generally gives us 300 Kelvin only. Okay. So, and how to calculate this entropy generation? Entropy generation is nothing but change in entropy of all interacting system. Okay, change in entropy of all interaction system. So this irreversibility can be calculated as this T naught is 300. Now, how to calculate this in all interacting system? Now, if you consider this as a universe. See here, this is the method to calculate entropy generation. Okay, this is the method only. Okay, so in every process we can apply the same method. So here is a source, here is a heat engine, because in heat engine there will be some fluid which is flowing, and that is flowing in a cyclic manner. Okay, that fluid is flowing in a cyclic manner. So for a cyclic process, we know that change in any property is zero. For any cyclic process, change in any property is always zero. So for this particular heat engine, that is whatever the fluid is flowing inside the heat engine, the change in entropy, or like it's a change in any property, that means your change in entropy will be zero. Okay, so for this particular heat engine, that whatever the fluid is flowing inside this, for that fluid, I can write the change in entropy is zero. Okay, so now we have one source and we have one sink. Okay, so now if you talk about how to calculate this entropy change for the source, because see here, change in entropy for all interacting system means change in entropy of source plus change in entropy of the heat engine, that is whatever the fluid flowing inside that heat engine, plus change in entropy of sink. Okay, so this is zero because it is following I can say that it is following some cyclic process. How to calculate the change in entropy of source? Because it is a reservoir, sink is also a reservoir, so it is rejecting some heat. So this I will be 300 into it is rejecting some heat. How much rejecting? 500. At what temperature? 1200 temperature. Plus change in entropy of the sink. Now how to calculate change in entropy of the sink? It is accepting some heat. See, the source is rejecting now, so it will be minus. So sink is accepting some heat. So how much heat it is accepting? Q2. So first of all, you need to calculate Q2, right? So if you apply the first law for the engine, 500 minus 180, Q2 will be how much? 320 kilowatt. Plus 320 by at what temperature? 300 temperature. So when you calculate this, you will amazed to know that yes, you will be getting 195 kilowatt here also. Okay. So your entropy, why we calculate entropy generation in a particular process? Because this entropy generation gives the amount of unavailable energy or amount of loss of available energy or amount of irreversibility in a particular process. So that's why we study this entropy generation. That's why we need to calculate entropy generation in any process. Okay, so that is the physical concept of this entropy. Okay, because what happens in the books when we study the entropy now, so at the time we don't get the physical significance of the entropy because it is completely connected with the available energy. It is completely connected with the available energy. You know? So that's why I have given you this particular example. I have given you this example and I have proved that yes, irreversibility in a particular process is nothing but T naught delta S generation. Okay, so we have calculated irreversibility with the help of concept. That is, what is the irreversibility or what is the loss of available energy? That is the maximum work we can extract, and whatever the actual work the system is producing, the difference between these two is the loss of available energy. Okay, because that work is lost due to irreversibility. Because suppose your system is able to produce maximum as 50 kilojoules, but due to some reasons it is only producing 45 kilojoules. So where is 5 kilojoules is going? It is getting lost. That is the loss of clear-cut available energy, right? So this loss of available energy is nothing but irreversibility. Okay, or this is loss of available energy, or I can say irreversibility. We can calculate by two methods. That is W maximum minus W actual, or T naught delta generation. So that's why we study this entropy, so that we can calculate irreversibility associated in a particular process. So I hope you are getting some kind of clarity that why we study entropy. Okay, so I'm hoping that you are getting some kind of clarity that why we study entropy. And whenever we need to calculate the entropy generation, so you just need to calculate the change in entropy of the universe, because you can see here the entropy generation. Where is entropy generation? This one. So whenever you want to calculate entropy generation or change in entropy of the universe, first of all, both are the same thing. Whenever you want to calculate entropy generation or you want to calculate change in entropy of the universe, both are same thing. Okay, so what you need to do, you need to consider a universe. So you need to calculate the change in entropy of the all interacting body in that particular universe. Okay, suppose there are 2 bodies, 3 bodies, 5 bodies, doesn't matter. You need to calculate change in entropy of each and individual system, and when you combine them, you will getting change in entropy of the universe, or change in entropy, or you can say entropy generation. Okay, so you need to understand that these are the same thing. That whenever we talk about entropy generation or whenever we talk about the change in entropy of the universe, These all are same thing. Okay, these all are same thing. So I hope you understood this particular concept. Okay. So now we are going to do some questions on the basis of these concepts. So let's say, first of all, we're going to see some solved numericals. Let's have this particular question. So please try this particular question. I'm giving you just 2 minutes of time so that you can read this particular question. First of all, read this question so that you will understand what is happening. Now, I will tell you the physical significance of this question also. Why is entropy is getting generated in this process? Okay, definitely, I will try to make you understand that why this entropy is generated. Okay, I will physically explain this concept. And please share the session. Yeah, please hit the like button also so that yes, we'll get some kind of motivation that yes, you people are loving these sessions. So definitely we'll try for the crash course also. And please share this session with your friends, yeah, so that they will also learn something about entropy, some physical significance of entropy. Please share this with your friends. So read this question, then we'll move further. Read this particular question, then we'll move further. I'm giving you 2 minutes of time to read this question. After that, we'll continue. After that, we'll solve together this particular question. Do you understand the concept of entropy? Yes or no? Have you understood this concept of entropy? That why we are going to study, why we are studying this entropy? Why? Because I tried to explain with the help of available energy or irreversibility. Have you understood the concept? Yes or no? All of you, the people, definitely some people will watch this session later. This particular question is for those people also. If they understood the concept of entropy with the help of available energy, please write yes in the comment section so that whenever I'll be getting this, whenever I'll be watching this particular session again, so definitely I'll read the comments. If you are writing yes in the comments, so definitely I'll be very happy that yes, you understood the concept of entropy with the help of irreversibility. Okay, as simple as that. Yeah, if you want to calculate the irreversibility, the concept is you need to calculate the entropy generation. That's it. Okay, so if you need to calculate the entropy generation, so why you are calculating this entropy generation? Because you are interested in the irreversibility. I will show you in this particular question. I will prove this in the particular question that yes, in this question definitely some losses are there, and thus that losses are represented by the entropy generation. Okay, I will show you in this particular question. Okay, so let's read this question. What is happening? Two blocks of iron and copper, both are initially at 80 degrees. So we have two blocks. One is of iron, one is of copper. Both are at 80 degrees centigrade. Okay. So are dropped into large lake. So beta, I'm requesting you once again that please share this session with the friends also, because understand this question and also understand so many with the help of this entropy. This particular question, they will definitely understand with so many things with the help of these questions. Okay, so two blocks of iron and copper, both are initially at 80 degrees centigrade, are dropped into a large lake. Feel this question. Feel this. Okay, suppose you have you have two stones, very big stones. One is of copper, one is of iron. Okay, so both are at 80 degrees centigrade. You have these two stones dropped into large lake. Suppose you are standing near a lake and you are dropping these two stones in the large lake. The mass of iron and copper is given as 50 and 20. So mass of these blocks are given. After a while, the system is in thermal equilibrium due to heat transfer between the blocks and the lake water. भैया जब इन blocks को पानी में फेंकोगे तो क्या होगा? ठंडे हो जाएंगे ना? Because lake is too large. So what will happen? You will throw this iron block and copper block in the lake. So what will happen? Due to the temperature difference, heat transfer will occur, and these will cool down up to the lake temperature, up to the surrounding temperature, definitely, because surrounding is lake only, right? So these will cool down. What will be the entropy change for this process? Now, try to analyze the situation. What is happening? Understand this. Whenever you are having two hot blocks or one hot block, whenever you are having a hot body, what you can do ideally, you can apply a heat engine between this hot body and the surrounding so that you can extract some work. Definitely, whenever there is a temperature difference between two bodies, whenever there is a temperature difference between two bodies, okay, so what we can do, we can apply what we can apply? We can apply a heat engine and we can extract some work. Okay, but here what we are doing? We are having two blocks, two hot blocks, we are throwing in the water. So that means we are not extracting any work. So definitely what is happening, if we have extracted that work in the initial, we have extracted that work, we would have something. मतलब हमारे पास कुछ होता अगर हमने work extract किया होता. But what we have done, we have thrown these blocks in the large lake. So what is happening? Heat is getting transferred and there is nothing. We are not getting anything. We are not getting any work. So that means the work which we could have extracted, now that is lost. Feel this question, but feel this question. Now the work which we could have extracted by the heat engine between these two things, that is the body and the surrounding. By applying a heat engine between the body and the surrounding, we can extract some work. So the work which we could have extracted, so that work we have not extracted, we have lost that work. So if we have lost that work, so that is called as irreversibility. Or I told you that irreversibility is nothing but the loss of available energy, which is calculated by the T naught delta H generation. So now, if you calculate the delta H generation in this particular case, it will come positive 100%, because yes, some work is lost. Are you able to understand this? Yes or no? Where irreversibility is there, na? Definitely, I told you that concept of irreversibility. So some irreversibility is there in this particular question. In this particular situation, some irreversibility is associated because that work is lost. So definitely entropy generation will come into the picture. Yes or no? Are you able to understand this? Yes or no? So tell me in the comment section, are you able to feel this question? Are you able to understand this? What is happening in this particular question? So basically, we have a large lake. Basically, we have a large lake. Now we have a large lake, which is just 15 degrees centigrade. 15 degree means 288 Kelvin. Okay, which is at 15 degrees centigrade, which is at 288 Kelvin. So now the initial temperature of iron and copper, what we are doing, we are throwing some iron block in copper block. So let's say this is iron block and this is a copper block. Iron, this is copper. We are throwing these two blocks in the large lake. We are throwing these two blocks in the or I can say in the large lake. So the mass is given, mass of copper, iron is 50 and 20. So it is having 50 kg, it is having 20 kg. So both are having initial temperature as Ti equal to 80 degree. 80 means 353 Kelvin. It is also Ti equal to 353 Kelvin. Okay, specific heat is given. For iron is given as 0.45 kilojoules per kg Kelvin, and for copper is given as 0.386 kilojoules per kg Kelvin. Okay, so now how we'll calculate this entropy generation? How we'll calculate this entropy generation? Because there are three bodies. If you see, because we need to calculate total entropy change, right? Total entropy change means what? Change in entropy of all the interacting system. Change in entropy of all the interaction system. So we have one iron system, we have one copper system, and we have a lake system. So we have basically three systems. So we need to calculate change in entropy of iron. We need to calculate change in entropy of copper. But this is not a gate question, okay? That's why it is lengthy. And change in entropy of the lake. We have to calculate these three things. So if we calculate change in entropy of iron, it is not a gate question. I'm repeating it again because it is a conventional question. If you see, it is a conventional question because there are so many things you need to calculate. So it is not a gate question. Change in entropy of iron. So in the heating or cooling case, how you will calculate change in entropy? That is MCL T final by T initial. See, just now we have written the formula here. In case of heating or cooling, MCL and T2 by T1, where T2 is a T final, T1 is a T initial, right? So MCL and T2 by T1. So it will be equal to M is given as for iron, M is given as how much? MM 50, 0.45. Final. What is the final temperature? Because it is coming in the thermal equilibrium with the lake. So final temperature will be 288. Or Ti, initial temperature is how much? 353. Okay, so when you calculate this, you will be getting as minus 1.579. No, sorry, minus 4.579. Minus 4.579 kilojoule per Kelvin. Okay. So now similarly, if you calculate change in entropy for copper, in the same manner, you have the mass of copper, you have the specific heat of copper, you have the final temperature of copper, you have the initial temperature of copper. Initially is 80 degree, that is 353 Kelvin. Final is 288 Kelvin. So mass of copper you will be having, specific you will be having, final temperature you will be having, initial temperature you will be having. You will be having minus 1.571 kilojoules per Kelvin. Okay. Now the question arises how you will calculate change in entropy of this lake, because if you see the lake is a large lake. So whenever you talk about large lake, it acts as a reservoir, because when you are throwing a small stone or a small block of 20 kg or 50 kg into a lake, but does it make any difference in its temperature? Suppose you have a large lake, you have ocean, okay, you have an ocean, and you are having a 100-degree centigrade ball, and you are throwing that 100-degree centigrade ball in the ocean. Does it make any? Will it create any difference in the temperature of the ocean? Absolutely no. There is so that's why if you see the large lake or large pond or anything surrounding, so they act as a reservoir. So doesn't matter how much amount of energy you are adding, its temperature doesn't change. So it is acting as a reservoir. So for the when it is acting as a reservoir, so it is losing heat, it is going to the surrounding Q iron. Surrounding means lake. It is also losing heat, Q copper. So it is going to the lake. Okay. So it is accepting these two heats. So means for the large lake, it is heat addition. Okay. For the large lake, it is heat addition. So the change in entropy is given as Q by what is the temperature of the lake. Temperature of the lake is 15 degree, that is 288 Kelvin. Now how you will calculate this Q? This will be equal to Q copper plus Q iron. So Q is given as MC delta T. So calculate this MC delta T for iron plus MC delta T for copper. Delta T will be same for both, because initial temperature and final temperature is same. Initial is 80 degree, final is 15 degree. So the temperature difference is 65 degree. Okay, mass and specific heat is given, and the surrounding temperature is also given as 288 Kelvin. So when you calculate this, you'll be getting the value of 6.820 kilojoules per Kelvin. Okay. So now you have the value of delta is iron, you have the value of delta is copper, you have the value of delta is lake. So what we need the total entropy change for this particular process. We need the total entropy change for this particular process. How you will calculate total entropy change? Add all these things. So when you add, see, definitely it will come positive, because I told you the scenario in the beginning. Because what is happening, we are losing some available energy. So when we are losing some available energy, that means that is irreversibility, or that means some delta is generation, entropy is generated. So that entropy generation must come positive. Okay, it cannot be a negative value. If you're getting the negative value, that means you're doing some wrong thing. You're doing some calculation mistake and some conceptual mistake. Okay, so definitely you'll be getting some positive value. So here, this cannot be the correct answer. This cannot be the correct answer. Absolutely. Okay, so when you add these three things, 6.820 minus 1.571 and minus 4.579, so it will come out to be 0.670. It will be coming as 0.67. So that option C will be correct. Okay, that option C will be correct. So I hope you understood the scenario and you understood the situation, what is happening. Okay, and according to that, we have calculated this. So I hope you are getting my point. So now let's move to the next question. Let's move to the next question. This is the next question on your computer screen. So let's have a look at this question and try to do it. Just read this question once, then we'll solve it together. Okay, just read this question once, then we'll solve it together. Just read this question once, then we'll solve it together. I'm just giving you 1 minute of time so that you can read this question. And please, I'm telling you again, share this session to your friends also, so that they can learn from these questions. Right now, you can share with your friends, like your college group, your branch, on your WhatsApp group. If you're watching this session, definitely you must be a mechanical student. So you can share this particular session with your friends in your college group, so that they will also learn on that what is the physical significance of these questions. Okay, why this entropy is generated? Because I connected this entropy with the help of irreversibility, right? So if you are getting this point, so definitely you will be understanding. So please hit a like button for the session and share this session with your friends. Hurry up, guys, and read this question once, and we'll solve it together. Okay, so let's see what is given in this question. 300 liter of air initially of 120 kilopascal, 17 degrees centigrade is heated for 15 minutes by 200 watts resistance heater. See, but whenever there is a question in thermodynamics, try to understand the physical significance of that. See, all the thermodynamics questions are taken from the real life examples. So it is just like the 300 liter of air initially at 120 kilopascal, 70 degrees centigrade is heated for 15 minutes by 200 watts resistance heater. So suppose you have a bucket, okay, closed bucket. Suppose you have a closed bucket and you have put some heater. So water heater, if you have seen water resistance heater in the winter time, because I belong from Rajasthan, right? So we generally use these kind of heater to heat up the water. So if you have seen the resistance, that is resistance heater only. So ठंड में जो पानी गर्म करने के लिए rod use होती है ना, that is called as resistance heater, है ना? So instead of heating the what I can say, instead of heating of water, instead of heating the water, we are heating air here. That's it. Okay, so in an insulated piston cylinder device, so we have a piston cylinder device in which we are heating the air with the help of some resistance heater. The pressure of the air is maintained constant during the process. Okay, what will be the entropy change of the air of constant specific heat? Sorry. So let's say we have a piston cylinder assembly. So first of all, you need to understand what is the meaning of constant pressure process. So if this is a piston cylinder assembly, and when I say pressure is constant, see, try to understand what is happening. Try to understand what is happening. There is some resistance heater like this. Okay, so there is some air. So when you are supplying electrical energy to this heater, okay, when you are heating the air, okay, so basically what you are doing, you are heating the air with the help of this electrical heater. Okay, you are heating the air. So when the air will heat it, so what will happen? Its pressure will rise. Okay, but what they said that the pressure remains constant. So if the pressure is rising, so to balance the pressure, what will happen? This piston will start moving up. Okay, then only the pressure will remain constant. Otherwise, how pressure will remain constant? So for the constant pressure process, this piston will definitely moving up. In only this is the only possibility in that the pressure will remain constant. Suppose when the pressure is increasing inside the this particular piston cylinder assembly, so due to that increase in pressure, this piston will feel some force and it will move because there are no stops, right? There are no stops, so it will move and it will balance the pressure. So definitely it will move upward, and let's say it is the final condition is coming like this. Okay, to balance this pressure, the final condition is coming like this. So it is the initial position and it is the final position. And air is generally assumed as an ideal gas. Okay, so whenever the air is given, we have always assume air as an ideal gas. Okay, so what we need to calculate? We need to calculate entropy change of air. So we have so many formulas for air, right? Change in entropy of air. See, if they are talking about the constant pressure process, okay, so see here, there are so many formulas for air. There are two formulas basically. So the first formula was for air, change in entropy. If you want to calculate the change in entropy of air, S2 minus S1 equal to m Cv ln T2 by T1. See, whenever there is Cv, there will be positive sign, plus m R ln P2 by V1. Also, it will be equal to m Cp ln T2 by T1 minus m R ln P2 by P1. Okay, so here they are talking about constant pressure. So whenever they are giving a constant term, take that formula in which that particular term is coming. So that means we'll be taking this formulas. Why? Because here pressure is constant, so this one will become 0. Because P2 by P1 will be equal to 1 and log 1 will be 0. So your change in entropy will be easier to calculate. S2 minus S1 will be equal to m Cp ln T2 by T1. Only you need to calculate this. So this will give you the change in entropy for air. Okay. So let's see, calculate. Let's calculate. So you need to calculate m Cp. They have given directly 1005 kilojoules per kg Kelvin. Okay. You need to calculate T2 and T1. T1 they have given. T1 how much? How much? If you see the T1, 17 degrees centigrade. That is 290 Kelvin. T1 they have already given us 290 Kelvin. T1 they have already given us 290 Kelvin. And Cp is given us how much? 1.005 kilojoules per kg Kelvin. They are given in joules, but they are asking final answer in kilojoules. So I'm taking this particular term in kilojoules. Okay, doesn't matter. Now, question arises how to calculate this T2, because you need to calculate this. And how to calculate this mass? So mass is very easy to calculate because this applied idealized equation P1 V1 equal to mR T1. Now, what is the initial pressure? They have given initial condition like 120 kilopascal, 300 liter of air. So P1 is 120 kilopascal. Volume is 300 liter, that means 0.3 meter cube. M. R for air is 0.287 kilojoules per kg Kelvin. Into T1 is 290. So from here you will be getting the mass of air. So mass of air is approximately 0.4325. 0.4325 kg. Okay. Now only unknown is T2. How we will calculate T2? See here what is happening. Try to understand. See, I'm not applying the first law. I'm just telling you the concept. How you can calculate this T2? What is happening? Try to analyze this. Due to this energy transfer, some work is transferred inside this air. Some work is transferred definitely inside this air. Some work is transferred. So due to this transfer of work, what is happening? See, work is a form of energy. You know, right? Work is a form of energy. So due to this transfer of work, what is happening? The gas is expanding. Or I can say, due to this transfer of work, the internal energy of the gas is increasing. Due to this transfer of work, the internal energy of the gas is increasing, right? Due to this transfer of work, the internal energy of the gas is increasing, right? Also, some work is done. So just try to understand what is happening. If I apply the first law of thermodynamics here, if I just apply the first law of thermodynamics here, okay, or if I apply the energy conservation, because first law of thermodynamics is nothing but the energy conservation only. First law of thermodynamics is nothing but the energy conservation only, right? So when you apply here first law of thermodynamics or the energy conservation, so we are generally students are aware about the first law of thermodynamics. They generally del Q equal to du plus del W. They don't worry much about the energy conservation. They are just familiar with the first law of thermodynamics. So we'll be applying first law of thermodynamics only. Okay. So now here, when you apply first law of thermodynamics, del Q equal to du plus del W. So here it is given as insulated. Water resistance heater is an insulated piston cylinder device. So insulated means there is no heat interaction. There is no heat interaction. So the change in, or I can say del W can be written as minus du. Okay. Now this work is done on the air. Okay. The work is done on the air because work is coming from outside, right? So it is the work done on the system. So whatever the work is coming, that will be negative work because work is done on the system. So whatever the work is coming, that will be the negative work. And this is the electrical work. So electrical work is given as I square RT. Okay. So they have given I, yes. Sorry, they are given directly this power of they have given directly the power. Okay, they have given directly the power into time. So we can calculate this into power into time. Okay, minus mCV delta T. Delta T means T2 minus T1. Okay, mCV delta T, T2 minus T1. So this power is given as 200 watts, and it is or we can say this energy is supplied for 15 minutes. Energy is supplied for 15 minutes. So this will be minus will be cancelled out. 200 into 15 into 60. So this will be the total energy transferred by the work into the system or into the air. This is a total energy transfer or total energy transfer or work transfer, you can say, into the air due to this resistance heater, or due to which what is happening, internal energy is increasing, right? So mCV T2 minus T1, M we have calculated, CV we have already known, T2 it is the unknown, T1 we have 290 Kelvin. So from here we will be having the value of T2. So you can calculate the value of T2 from here. So when you will be getting the value of T2, so put the T2 here. When you will be getting the value of T2 here, so put the T2 here. So you'll be getting the final answer. Okay. So we have calculated mass, we have calculated T2, and then we'll be getting the final answer S2 minus S1. Okay. Change in entropy we'll be getting. Okay. So if you see the questions of entropy, so generally those are combined with the first law of thermodynamics and ideal gases equation. So whenever there is a question of ideal gases, so definitely there are 2-3 things only. Yeah. So whenever there is a question you will see from entropy, there is only 2-3 things. Whether it will be solved with the help of first law of thermodynamics, whether it will be solved with the help of ideal gases equation. That's it. Okay. So no need to worry. Thermodynamics is a very easy subject. Okay. You need to understand that how to connect the things. If you are able to understand that how to connect things, definitely you will be able to understand thermodynamics completely. Okay. Because it's like a chain. First we study the basic concepts, then first law of thermodynamics, then second law of thermodynamics, then entropy, then available energy, right? So it's like a chain. So whenever you miss a single or I can say chain में जैसे बहुत सारी कड़ियां होती है, whenever you miss a single कड़ी or single portion of the chain, so that is not useful. Okay, there is no use of that. So try to understand that whenever you are going to study thermodynamics, please understand each and every chapter of the thermodynamics, then you will find it easy. Otherwise, if you're not studying the first law and you're directly entering into the second law, you will find it tough. Suppose you're not studying the first law and second law, you're direct entering into this entropy or available energy, you will find it more difficult. Oh baba, what is happening? So definitely you must start from the basic, right? So let's move to the next question. So now we are coming with a gate question. We will be coming into the gate question. So this is the gate question for you people. It's a very simple question. Just I'm giving you 1 minute to read this question, then we will solve this. It's a very simple question. Huh? It's a very simple question. Just read this question, then we'll solve this together. And I'm telling you again, please share this session with your friends so that they will also get some benefit of this particular session. We are doing this just for you people, yeah, so that in the last time you will get some revision of these important concepts. If you have any doubt, you can definitely ask in the comments. If you are watching this live, then you can ask now, and if you are watching this later, definitely you can ask later these comments. Okay, so what is given in the question? It is a very simple question. You can see that a closed system contains 10 kg of saturated liquid ammonia at 10 degrees centigrade. Saturated liquid ammonia, okay, at 10 degrees centigrade. Heat addition required to convert the entire liquid into saturated vapor. So means we are converting saturated liquid to saturated vapor. So it is a phase change process. First of all, we are converting saturated liquid to saturated vapor. That means it is a phase change process at a constant pressure of 16.2 megajoules. At a constant pressure of 16.2 megajoules. Okay. If the entropy of the saturated liquid is this, the entropy of the saturated vapor is what? In kilojoules per kg Kelvin. Okay. It's a very simple question. So basically, it is a phase change process. It is a phase change process. So in the phase change process, what we know? See, the unit is important, kilojoules per kg Kelvin. Okay. So I'm writing in kilojoules per kg Kelvin only. Okay, because we require final answer in kilojoules per kg Kelvin. So what I can write? Sg minus Sf equal to Hg minus Hf by T saturation. Now this, or I can say this latent heat, HFG. HF, this must be in per kg, kilojoules per kg, right? Because in the right side we are putting kilojoules per kg Kelvin. So definitely it must be in kilojoules per kg and it must be in Kelvin, right? Then the unit will be satisfied. Okay. So now they have given SF because they have given the entropy of saturated liquid. They have given this value. You have to calculate Sg. Okay, minus 0.88 equal to. Now how you will calculate this latent heat in kilojoules per kg? See, they have given total liquid is 10 kilojoules, 10 kg. Total liquid is 10 kg, and heat addition required to convert the entire liquid into saturated vapor. Heat addition required to convert the entire liquid into saturated vapor. That means the heat addition required to convert the 10 kg of saturated liquid into saturated vapor is 16.2 megajoules. Means 16.2 megajoules is required for 10 kg. So for 1 kg, how much required? 16.2 by 10 megajoules. So in kilojoules, it will be how much? 16.2 into 10 to the power 3 by 10. Okay, so this will be the amount of heat in kilojoules per kg will be required. Okay, 16.2 into 10 to the power 3 by 10. So that's what I'm putting here. Only you need to balance the unit, that's it. 16.2 into 10 to the power 3. It is in kilojoules. If you divide it by 10, it will be kilojoules per kg, and divide by temperature, that is 2, how much? 83 Kelvin. 10 degrees centigrade, no? That is 283 Kelvin. So when you calculate, this Sg will be 6.604 kilojoules per kg Kelvin. This Sg will be what? 6.604 kilojoules per kg Kelvin. Okay, this will be the entropy of saturated vapor. So only you need to balance the unit, that's it. Suppose if you are not dividing it by mass, so definitely you'll be getting the wrong answer. Okay, So only you need to balance the unit here. That's it. It is a very simple question of GATE exam. Okay, it's a very simple question of GATE exam. 2 marks question. It is 2 marks question. Only if you don't balance the unit, definitely you'll get the wrong answer. But if you balance the unit, you will get the right answer. This is the next question for you people. This is the next question for you people. Just read this question once. Just read this question once. Then we'll solve it together. It is one of the good question actually. It is one of the good questions from the thermodynamics. Just read this question once, then we will solve it together. Okay, so let's have a look what is given in the question. Two identical metal blocks L and M. Specific heat is given as this. Each having a mass of 5 kg are initially at 313 Kelvin. Okay, initially at 313 Kelvin. A reversible refrigerator extracts heat from block L and rejects heat to block M. Okay, so basically there is a reversible refrigerator which is acting between these two temperatures. So this is block L, this is block M. Okay, and there is a reversible refrigerator which is acting between these two blocks. Okay, so basically this is what this refrigerator is doing. This refrigerator is taking heat from the block L and is rejecting heat to the block M. Okay, so now initially the temperatures are 313 Kelvin. So it is also 313 Kelvin initially. It is also 313 Kelvin initially. So block M until the temperature L reaches 293. So what is given? Until the temperature is reaching 293 Kelvin. So what is the final temperature of block M? Okay. So the only thing we know here that it is a reversible refrigerator. That's it. It is the reversible refrigerator. We don't know anything about this. We know that it is a reversible refrigerator. That's it. Okay. And we need to find out the temperature. So how you will do? Because we know that is a reversible refrigerator. So for the reversible process, definitely it will follow reversible process. So what we know for the reversible process, that the entropy generation will be 0. That's it. This is the only thing we know for the reversible things. Or entropy generation, what we can write, the change in entropy of universe will be 0. So let's have a look with the help of this. Maybe we can get something, because we don't have any other information in this particular question. We don't have any other information, because if you calculate, see, because they have not given the work also. Right? So how we can calculate? Okay, so definitely what we can do, we know that yes, entropy generation will be 0 because it is a reversible refrigerator. So let's try to do some experiment with the help of this change in entropy of universe. Okay, so what is happening in the universe? If you observe the universe, see, I told you how to calculate change in entropy of the universe, just like this, because it is having some block M, and it is having some fluid which is flowing in the refrigerator. Okay, so that means your change in entropy of block M plus change in entropy of block L plus change in entropy of the fluid which is flowing in the refrigerator. This must be equal to 0. So this will be equal to 0 because why? Because the fluid is flowing in a cyclic process, and for the cyclic process, change in entropy is 0, right? For the block M, how I can write? Because block M is heating, its temperature is definitely increasing because some heat is supplied to this block. So it is a heating process. So MCLN T final by T initial. What is the T initial? 313. Plus, what is the change in entropy of block L? That is MCLN T final by T initial. T final is 293, T initial is 313 because it is a cooling process. So entropy associated during heating or cooling is what? Like this, MCLN T final by T initial. This must be equal to 0 because both are having the same mass and both are having the same specific heat. It is given. See, both two identical metal blocks, specific heat is same and each are having the same mass. So MC we can take common and it will go there and it will become 0, right? So from here I can write log TF by 313 plus log 293 by 313 must be equal to 0, right? So what we can write, it will be a log A plus B. So I can write log A into B, that is 293 TF divided by 313 square, which will be equal to 0. So now if you take log here, so it will become e to the power 0. E to the power 0 is 1 only. So 293 TF will be equal to 313 square, and TF will be equal to 313 square by 293. So it will be 334.36 Kelvin. Now the confusion is what? Now there must be confusion in your mind, sir. Why we cannot do like this? Because it is a reversible refrigerator. Whatever the amount it is rejecting to this refrigerator, it is supplying to this refrigerator. That same amount of heat, definitely it will supply to the block M. There must be a question in your mind because they have not given the work, right? There must be a question in your mind because they have not given the work interaction. So definitely whatever it is extracting from the block L, it must go to the block M. And if you calculate by this, that heat taken by the block L, it will be equal to heat given to the block M, and the TF will come to be 313 Kelvin. So this is the biggest mistake you can do, because it is the violation of the Kelvin-Planck statement of second law. Why? Because according to the Kelvin-Planck statement of the second law, what is the statement? What is the Kelvin-Planck statement of the second law? That there is no any device possible which can extract heat from the lower temperature and transfer heat to the higher temperature without any work doing on it, or without any other energy interaction. भैया बिना वर्क किए आप हीट को सप्लाई कैसे कर दोगे? इसको कहां पे भूल गए, है ना? So if you are taking directly that yes, heat rejected by the block L will be equal to heat gained by the block M, no, it is not possible, because definitely there will be some work, whether it is a reversible refrigerator or it is a irreversible refrigerator, there will be some work definitely. So this Q2, let's say this is Q1, this Q2 will be always greater than Q1. Otherwise, it will be the violation of the second law, that is Kelvin-Planck statement. It will be the violation of the Kelvin-Planck statement if you take it equal. So that means without doing any other work, you are taking heat from the lower sink and you are transferring to some higher source. Okay, sorry, you are taking some heat from the lower temperature and you are transferring this to the higher temperature without doing any other work. If you take Q1 equal to Q2, so that's why it cannot happen. Are you getting my point? Okay, so this must be clear. This must be clear to you, that you cannot take both the heat interactions as equal. Okay. So this is one of the beautiful question in the GATE examination. So now we'll move towards next question. So it is a common data question. If you see the next question, it is a common data question actually. I think it came in 2011, 2012, because before 2010 only, these kind of questions used to come in the exam. Okay, and these are very good questions actually. And it is very simple question also. It is one of the best question and very simple question also. See, I will try to explain you that why Carnot has selected isothermal processes in its cycle. With the help of this particular question, I would try to explain why the Carnot, Sadi Carnot, he has taken isothermal processes in his cycle, because he knew something which you don't know still, which we still don't know. He knew something. So now I will try to explain what he already knew at the time when he was making his cycle. So just read this question once, then we'll move further. Just read this question, go through this question once, then we'll move further. Just read this question once. And here we need to calculate for universe. Because system definitely will calculate, because you know the formula, definitely you can calculate for the system. So I'm making it more typical for you, for universe. One more easy, actually more easy. So let's say what is given in the question. Let's see. Nitrogen gas, which is having some molecular weight 28, is enclosed in a cylinder by a piston at the initial condition of 2 bar, 298 gallon, 1 meter cube. In a particular process, the gas slowly expands under isothermal condition. So it is isothermal expansion until the volume becomes 2. So V2 is given as 2 meter cube. Heat exchange occurs with the atmosphere at 298 Kelvin during the process. So the process itself going on at 298 Kelvin, and the surrounding is given at 298 Kelvin. So basically you have piston cylinder process in which some expansion is going on, and this gas inside this piston cylinder process in this piston cylinder is at 298 Kelvin, and also heat transfer is occurring at 298 Kelvin. So the process is occurring at 298 Kelvin and surroundings also 298 Kelvin. Okay. Now try to understand what is happening. The first question, the work interaction for the nitrogen gas. Actually, this question is coming from the first law of thermodynamics. So when you apply the formula, that the work interaction for the isothermal process given as P1 V1 log V2 by V1. So what is P1 is given as 2 bar. So we need answer in kilojoules. So 2 bar will be 200 kilojoules. Sorry, kilopascal. V1 is 1 meter cube log 2 by 1. So it will be coming as 138.6 kilojoules. So this will be the correct answer. Okay. Now try to understand what is happening. This is the isothermal expansion process. Okay, this is the isothermal expansion process. Your temperature is not changing, right? It is isothermal expansion process. Your temperature is not changing when the temperature does not change. Definitely you'll be getting this PDF. Don't worry. Definitely you'll be getting this particular PDF. Don't worry. Okay. So when your temperature does not change, so what happens? Try to understand what is happening in this. When P1, this work done we have already defined. Okay. So try to understand what is happening in this particular process. See, this isothermal expansion is going on. Isothermal expansion is going on. So what is happening in this particular process? When the process is expanding, when the gas is expanding, it will lose its temperature because definitely it will try to cool. In the expansion process, gas cools, right? We know that in the expansion process, temperature decreases, right? When it is expanding, its temperature is decreasing, right? At the same time, some heat is transferred so that its temperature is remaining constant. So this is the funda of the isothermal process. Okay, this is the funda of the isothermal process. What happens when the gas is expanding? When the gas is expanding, it will try to decrease its temperature. Whenever the gas expands, its temperature decreases. So when the gas is expanding, its temperature tends to down. But whenever the temperature is down by small amount dT, at the same time, heat is transferred to the system so that it can maintain the isothermal condition. So this is the funda of the isothermal process, right? This is the funda of the isothermal process. So now what is happening in this particular process? Heat is transferred from the surrounding to the system. Heat is transferred from the surrounding to the air. Okay, I am trying to explain you this particular question with the help of concept. I'm not going with the formula. I am trying to explain you this particular question with the help of concept that what is happening in this particular process. That when the gas is expanding, its temperature is going to down or its temperature is going to decrease. So when the temperature is going to decrease a small amount dT, at the same time some heat is transferred so that it can maintain the isothermal condition. Okay, I hope you are getting my point that yes, how it can maintain the isothermal condition, because whenever it is expanding, it will its temperature is going down, and when the temperature is going down by a small amount dT, some heat is transferred from the surroundings so that it can maintain the isothermal condition. Okay, so now what is happening? Some heat is added in this process, and from where this heat is added? From the surrounding. Okay, so for an isothermal process or for a reservoir or for a phase change, how the entropy change can be calculated? Q by T, because there is no temperature change, right? There is no temperature change. So how you will calculate the change in entropy? Q by T. So we know what we know. We know that for isothermal process, del Q equal to du plus del W, right? So du is 0. Du is given as mCv delta T. Du is given as mCv delta T. So for isothermal process, delta T is equal to 0. So you'll be getting del Q is equal to del W for isothermal process. So now in the first part, we calculated del W. Okay, so we know that del Q will be same. So this del Q will be 138.6 kilojoules for this gas. For this gas, del Q, and this is heat addition. I tried to explain with the help of concept. This is definitely heat addition, and it is coming positive. When it is coming positive, it is always heat added, right? So this heat is added to the gas. From where it is, from where this heat is getting sorry, from where this particular heat is getting added? From the surrounding, right? From the surrounding. So for surrounding will be negative minus 138.6 kilojoules. Now we need to calculate change in entropy of the universe. How we will calculate? That is change in entropy of the gas or the system plus change in entropy of the surrounding. Now, what is change in entropy of the system? Because it is a heat addition, right? Heat addition at constant temperature, whether it is a reservoir, a phase change process, or a constant temperature process, it can be given as Q by T only. So it is a heat addition, so plus Q by T. So plus 138.6 by T. What is the temperature? 298 Kelvin. This is the change in entropy of the system, that is change in entropy of the gas. Second, what is the change in entropy of the surrounding? Surrounding is rejecting the heat. That is minus 138.6 by at what temperature? At 298 temperature. So it is coming as 0. So the change in entropy of the universe is coming as 0. Now, try to understand why Carnot has taken the isothermal processes in his cycle. Because he already knew in the isothermal process there is no entropy generation. This change in entropy of universe is what? This is nothing but this is the entropy generation in a particular process. So why Carnot has taken isothermal process in the cycle? Because it is a completely reversible cycle, completely reversible process. So because there is no entropy generation in the isothermal process, right? So there are two isothermal processes in the Carnot cycle, and there are two reversible adiabatic processes in the Carnot cycle. So for the reversible adiabatic processes, we already know that there is no entropy generation because we are already set reversible, right? So there is no entropy generation. And when we are talking about the reversible isothermal processes, there is also no entropy generation. So the entropy generation in the entire cycle, that is a totally reversible cycle. That is a totally reversible cycle. So that's why Carnot has taken the isothermal processes in his cycle, because he already knew there is no entropy change in this isothermal processes. So that's why that is a totally reversible cycle, because there are no losses associated. How it can be possible? Because all the processes are reversible, internally reversible. There are no losses, right? And externally reversible also, because there is no irreversibility coming from the external surrounding or something. Okay, so that's why it's a he has taken isothermal processes, right? So I hope you understood this. See, this is the method I told you with the help of concept. If you want to go with the help of formula, you can go. That is change in entropy of the system, change in entropy of the gas. I told you so many formulas to calculate the change in entropy of the gas. So you can apply that formula. And what is the change in entropy of the surrounding? Change in entropy of the surrounding you can calculate by this only. Okay, that is Q by T. So whether you can go with the help of formula also, then also you'll be getting the same value. Don't worry. Okay, then also you'll be getting the same value for sure. So let's have a last question for this particular session. Then we'll be ending this session. So this is the last question for this particular session. So let's, I'm giving you 1 minute of time so that you can read this question, then we'll solve this together. Okay, so just read this question once. I'm just giving you 1 minute of time. It is a very simple question. Huh? It is also a GATE question. It is a very simple question. Only you need to understand the concept of entropy. That's it. If you understand the concept of entropy, you can calculate entropy change in any process for any system. Doesn't matter. Okay. Digital class room is better than this one, sir. Okay, so don't worry. We will take tomorrow's session on digital board only. Okay. For tomorrow's session, I will be taking on digital board only. Okay. Just because you are requesting that now, so that's why. See here in this particular session also, what when we use that Zoom and this OneNote, so it is convenient for us to sit in this in the sitting position, and we are taking the session. So don't worry. So I'll be taking tomorrow's session from the studio only. Okay. So in the digital board, if you love this, love that digital board, so I'll be taking that session from the digital board only. Okay. Okay. So let's see what is given in this question. An electric current of 15 ampere is maintained for 1 second in an electrical resistor of 10 ohm. So they are talking about one resistor. So let's have a resistor. This is a resistor. Okay. What is happening? Some 15 ampere current is flowing. Okay. Is maintained for 1 second. Time is given as how much? 1 second. And resistance is given how much? 10 ohm. If the temperature of the resistor is maintained at constant, or your temperature is maintained as constant at 30 degrees centigrade, that is 303 Kelvin. Okay, temperature is maintained at 30 degrees centigrade equal to 303 Kelvin. The entropy generated during this process. Okay, the entropy generated during this process. Now, why? First of all, you need to understand that why this entropy is generating, because some electricity is flowing in this resistor. Now, what is happening whenever there is some irreversibility? Because see, electrical work, it is the I can say it is the highest form of work we are having, because we can do so many things with the help of this electrical work. We can run the fan, we can run the AC, we can run so many things, appliances. So it is a high grade energy. It is a high grade energy, right? So when we know it is a high grade energy, that work is the high grade energy, right? So we are not utilizing it, we are wasting it. Why? Because when the work is flowing in this resistor, when the work is going in this resistor, so due to the heating effect, the heat is lost in the surrounding. Okay, work is converted into heat, and that heat is lost in the surrounding. So we are wasting that work. That means we are wasting the available energy. We are wasting the available energy, means irreversibility is coming into the picture. So definitely there will be some entropy generation. Definitely there will be some entropy generation for sure. Okay, so that's why entropy generation is coming into this picture. So now, how much entropy is generated? So let's say this resistor as a system. Just a second. Let's say this particular resistor as a system. This is your system, and there is surrounding also. So if you want to calculate entropy generation, yes, Gautam, your answer is correct. Very good. So entropy generation is nothing but change in entropy of the system plus change in entropy of the surrounding. Now, what is happening with the system? See, whenever there is a heating process, cooling process, how we calculate MCL and T2 by T1. But here temperature is maintained as constant. So if you apply that MCL and T2 by T1 for this, so this T2 by T1 is same now because temperature is maintained constant, so it will be 0. Or you can understand by this, because temperature is maintained constant with respect to time. That means your resistor is at steady state. When the resistor is a steady state, so that means your change in any property with respect to time is 0. So entropy change is also 0, right? So your system change in entropy of the resistor is 0. Now, what is the change in entropy of the surrounding? Because this resistor is losing some heat to the surrounding, and surrounding is having a temperature of 30 degree. Because it is not given, so we can take the 30 degree only, because there is no other temperatures given, so we can take 30 degree means 303 Kelvin. So how you can calculate this Q? Because whatever the electrical work is, or whatever the electricity is flowing, so due to that electricity, some heat is generated. So what is that heat? That is I square RT. Okay, so this is equal to Q. So this heat is lost to the surrounding. Okay, so this heat is lost to the surrounding. For the surrounding, it is heat added. So it will become plus Q by 303. So Q is how much? I square RT. I is 15 square into R is 10 ohm, and time is how much? 15 by T, 303. So when you calculate this, you will be getting 7.43. Okay, you'll be getting 7.43 joules per Kelvin. Okay, this will be the answer. So I hope you understood this, and I hope you enjoyed this session, because I have tried to connect all the things with the help of irreversibility. That is a topic of available energy actually. So I hope you understood the concept of entropy, that why we study entropy and why we calculate irreversible, why we calculate entropy generation, because that gives us irreversibility. That is the losses in actual processes. Okay. So I hope you enjoyed the session, and tomorrow we are having a session in which we are going to discuss Brayton cycle, which is one of the most important topic of the applied thermodynamics. So yes, please be there in tomorrow's session, and please tell your friends also, so that they can also attend that particular session, and they will also enjoy that, because tomorrow you are going to see Brayton cycle in a different manner. I will tell you so many things about the Brayton cycle, that why regeneration is done, why that reheating or intercooling is done, and I'll be telling you so many things about the Brayton cycle. So please be there in tomorrow's session. So आज के लिए इतना ही, आज की सभा समाप्त करते हैं. So we'll meet tomorrow in studio, because I got some request from some person so that they will understand more in a better way in studio and digital board. So I will take tomorrow's session from the digital board. Okay, so bye bye for now, and good night. We'll meet tomorrow. Bye bye. Good night, everyone.